Up next is Andrei Berar of Amkor in the creative cooling techniques for package level testing area. Andrei joined Amkor in 2018 and is Senior Director for Test Business Development, WW Test Services. Prior to joining Amkor, Andrei worked at KYEC USA for 7 years as Executive Director for Sales and Marketing with responsibility for test services and business development in North America. He holds a master's in mechanical engineering from Polytechnic Institute Romania and an MBA from Pepperdine University. Please welcome him. Go ahead, Andrei.
Thank you much, Rob, for the introduction, and good day to everybody. I'm very excited and pleased to be here today in front of you. Actually, probably I'm in your face. Also, I have to confess I was very lucky in my 30+ year involvement with tests. I was able to keep most of the times those chips below the magic 150 C for junction temperatures. So otherwise will not be able to talk about tests, but we'll be talking about fried chips. I would like to present 5 topics that I'm convinced that will steer your interest, and you'll be able to walk away with some nuggets of knowledge that you can readily use and apply in your daily life. Maybe it will solve some of your problems that keep you awake at night. So I'll be talking about thermal management challenges, power dissipation roadmap, high power devices, how to manage the test temperature, MEM sensor and the memory devices, temperature control, and I'll close with a summary. Power, electrical power, makes our silicon embedded dreams come a reality. That really allow us to communicate through all these little magnificent devices that for now I hope you turn them off for my presentation. A direct consequence of power is power dissipation. And power dissipation presents itself in all devices, no matter what market they use for, what size they are, what performance, what price they are. So you'll see from left to right, high power computing devices, many cores, 56+ core, high power dissipation, but you also see that in the large mobility devices, smartphone, tablets, lots of IoT that most of us use every day, also in industrial, and definitely in automotive that become more and more electronics than mechanical parts. So we deal with power dissipation on everything that we touch. And one thing we definitely we should be aware of, that not managing the power dissipation properly could be very damaging. We can lose our devices much faster than, I will say, security virus can take care of them. So with that, what a better way to move on and figure out what do we need to manage than providing a roadmap where we are and where we're going with this power and power dissipation. We can look at the power dissipation roadmap and segregate it in probably three buckets with some gray area in between. I'm talking about under 10 watts power dissipation for mobile devices, wearables, IoT, laptops, automotive, industrial, even some laptops or desktops, under 50 watts, but it's a big daddy of all. It's over 125 watts. Now it's considered high power dissipation. And as we're getting into larger devices, smaller geometry, that means a higher leakage, which create a lot of power dissipation. We are moving into hundreds of watts of power dissipation. Expectation will be more than 1,000 watts in a near future for edge computers, switches. So this is what's ahead of us, and we know we need to deal that for sure, and we'll talk about that in the next slide in the final application. But we need to test these devices, make sure they're going to make it to the final application. So we need some creative thermal management solution that we'll be talking about soon. So this is what the rubber meets the road, and I'm going to stop with the final application, saying a few words. It's very critical to keep those devices cool in the final application, but there are a lot of already well-known methods to do that. A lot of work was done. I believe it's very well under control at this time. Start from simple air cooling to dipping boards and parts in liquids. So this application, they are well known and well managed. For sure, they're going to need to have their own roadmap how to address it. But if you look at the area before the final application, we're talking about assembly and test. And there are a lot of stringent packaging required. We mentioned, or I think probably almost every presentation before we mentioned heterogeneous integration with their challenges. So when it comes to test, we need to test these parts over a large span of temperature, minus 55 to 165, sometimes 200. We need to manage them in all level, from wafer sort of package test, the burning and system level test. And we need to put them more stringent condition that they're probably going to see in a final application. Make sure that we have a guard band when they're going to be in real life. So we're looking at some way of a short-term solution to exercise dynamics devices that need to be tested beyond their normal expectation in final applications. Thermal management for high power devices. There are plenty challenges. High power, 150, we need to keep the temperature control over minus 55 C to plus 150 C. And again, wafer level, final test, system level package. For MEMS, sensor and memory devices, they also have a lot of power dissipation, but the challenges may be a little bit different. On one side, we're talking about multi-device tested in parallel, and we need to make sure we provide a site-to-site uniform temperature control, as well as they have some rapid temperature cycle requirements. And on top of that, we'll touch base a little bit. Sensor, they may need some other stimulus. We may need to mix temperature with gas, with pressure. So that makes our test life much more interesting. Also, we need to keep in mind, we need to be very cost conscious. So we need to manage our cost. That's we need to address our manufacturing processes. Thing that we monitor is liquid nitrogen, costly and a little bit dangerous. Reduce overall cost by minimizing footprints, providing very efficient chillers in order to address the cost and economic challenges. Regarding high power devices temperature control, I briefly mentioned there are primarily two vectors that provide power dissipation. One is the static power. This is the continuous leakage and smaller geometry, more leakage, and also the dynamic power that comes during switches. In package, and we heard that before, we try to take care of as much as possible of managing the temperature and temperature isolation. Copper plates become a common part of assembly. But when it comes to test, what we are facing, and again, the heterogeneous devices stick their nose here. We had hotspots, and we had hotspots because multiple chip devices on one side with different thermal characteristics. And we also have spikes. Spikes due to the way we apply the vectors during test. So our challenge is primarily considering all these spikes and different devices. We need to keep our junction and the case temperature, I would say around 125, 150 degrees C. So this is primarily the challenge in test. And it's not a one solution fits all. We have different devices, different size, different power that need to be managed. The primary thing that we need to provide is, as expected, for active power dissipation. We need active thermal control. We need to be right on top of the power dissipation. Probably we need to anticipate the power dissipation and the spikes. We're making some inroads to be a little bit more adaptive, predictive, the vectors are coming that creates the spikes. Overall, we should be able to manage that because we're in charge of when different vectors will be used. So if we couple with some artificial intelligence to our active thermal control system, we should be able to anticipate and be able to take care of most of the spikes as well as hotspots. Regarding the hotspots, one very important element is the fact that we need to provide the components that will touch the case. This is how we take the power out of the devices during test. So there are a few solutions. One is something like a compliant contact, a thermot compliant contact that makes a perfect mechanical contact with a very low thermal resistance. The most common solution are the Peltier thermal heads. And you see a variety of them, different shapes, and again, different shapes due to the fact that there are different type of devices, large, small, and also when we talk about heterogeneous parts, we may need to use more than one type of thermal head. On top of the thermal head, which is a part that makes contact with the device, we need to be able to remove the heat from the thermal head. And there are a variety of active thermal control solutions that are ready for high volume manufacturing for final test, as well as system level test. This one moved away from the traditional air cooling, which is running out of steam, sort of say, to more liquid cooling. So all this application, they use liquid cooling at the various level, use chilled liquid, and for most regions, a minus 55, we need to use refrigeration technique. So right now, there are well-known manufacturing proof up to around 1,000 watts to remove power through the thermal heads, moving towards 2,000, 2,500 watts solution. Again, the devices may not be at 1,000 watts, but we need to be prepared to take care of the spikes. So the spikes are required to overpower them. So we may need more than the device itself in normal condition dissipates. One thing I want to mention, we're very proud to use we don't use any liquid nitrogen, which again addresses our cost and makes our much more efficient. Heterogeneous solution, we have solution, but there are customized solution. We need to look at each particular device. Again, we may need more than one thermal head per device, and we start to implement some of those solutions already. We need to test these parts, like I mentioned, not at package test, but also more and more we need to test them in wafer. It becomes an increasing number of requests to test those colds. There are a lot of merits for testing these high power devices in cold temperature. IDDQ becomes a very important tool. So high voltage, multi-sites in parallel, low temperature, with the expectation that we can minimize the cost down the line, package only good devices, minimize the requirements for burning, and we need to do that for automotive for their stringent application. This solution as well, so cold solution as well as hot solution for
Andrei,
probing.
if I could interrupt a couple of questions.
Absolutely.
One of them is there a solution available for 1,000 watts now?
As I showed, there are solutions for 1,000 watts with this active controller. They may need to be customized based on certain needs. And it's something that we really need to pay attention, hotspots and spike, but there are solutions to do that now for final test.
Yeah. Hey, Andrei, so I'll add to that. So would you say though, so, I mean, 1,000 watts, say over a 50 millimeter of a 50 millimeter die versus that over a 25 by 25 die makes a difference though, right? So the power densities is really what creates problem.
No question about, again, the smaller the device, the higher the power, the bigger the problem we have. But we have solution, we customize them, which that makes a difference between test and final solution. So we need to work for specific device, but again, there are solutions and the more solution coming, need to watch out for the spikes and hotspots. That's a huge concern.
Yeah. Okay. Go ahead, Andrei.
I just want to mention the prop solutions. These are well-known solutions. They well embedded in everybody's test floor. So it's nothing here that stops us to use them. I just want to make sure everybody's aware we're well prepared with testing environmental wafers at probe, hot or cold.
Yep. So, and that's another question here regarding that. Do you see a need for active thermal control at the wafer level?
So far, we did not. Maybe the fact there are not so many heterogeneous wafers, but it's definitely a possibility. So it's something that we need to pay attention to.
Yep. And I think in order for that to be possible, though, you have to have kind of a chuck that can be sectionalized, control in certain spots. It's hard to move all that mass quickly. You have to have some kind of zone control.
Yeah, again, that will be something that may need to be customized as well, because not all the wafer will be the same. So it almost said we may need one chuck for one kind of wafer or some other way to customize a chuck on the fly for different temperatures. It's a challenge that I think the industry is ready to embark on when it's coming. So I didn't have the challenge yet, to be honest, but it's definitely a real possibility. I mentioned about sensor and memory. They have their own challenges. Again, maybe it's not so much power, but we are testing so many devices. We are looking 500 plus parts in parallel, and we need to make sure we can keep them into plus minus 1 degree C. Pretty soon, we may need to keep them into 0.5 degrees C. Again, over a large temperature range, possible we have to do that in one insertion, hot, cold, and cycling and moving fast between them. And besides temperature, we need some other stimuli that can be. They will start to mixing gases and different pressure. So it's in itself, it's a different challenge. There are solutions for that. So it definitely, we have up to around 256 sites in parallel. For MEMS sensor, we manage that. We have pick and place handler, turret handlers, specialized handlers. We use temperature chamber. We can drive also some mixes, gases, and pressure. We can keep almost plus minus 1 degree C. Beyond the 256, more into the 512 sites in parallel, we start to hit some walls. There are not well-known solution proof for high-value manufacturing. There are some concepts. Some of them they already proved, but not in high-value manufacturing. They may need to be standardized to reduce their cost. But there are some concepts that I'll present it briefly for both over 500, over 1,000 parts in parallel, and with higher uniformity down to plus minus 0.5 degrees C. But this is something that is still quite a lot of work to be done. Again, it's a matter of balancing not only the technology, but the economics of the technology. Sure, you can customize the solution, but you cannot afford it. So one concept, and again, it's a concept from the fact that, yes, it's proved, we move parts with that, but it's not ready for high value manufacturing. It needs to be implemented in a full process. So the core of this, this concept is in fact this flex tray frame, which practically can hold an infinite number of devices. It's just a matter how big you make this flex frame. And the flex frame is transported through this test station. It's a very compact test station that seals all around the flex tray. So the main advantage is you have all these hundreds of devices in a very tight control area. And that's the most important part. It's much easier to control the temperature and uniformity of the temperature in a tight control area. And each device, based on the manifold provided by this chamber, has this mini environment. So again, it's much easier. It's very easy to control the temperature. It's also very easy to change from cold to hot and cycle, because you control one device, you can overshoot the cold or hot and get you the right temperature in a matter of seconds. This also, through this manifold, allows you to combine pressure, different gases and temperature. So you can do a lot of things in one insertion, or you can decide to look at the more serial daisy chain solution with different station. But the concept is the same. You move these devices in this flex tray from one station to another. It comes to the station, and all of a sudden, everything is concealed, so easy to deal with that. More work on that, but they're already moving parts. So very encouraging.
So another question, Andrei.
Yes, sir.
How receptive are product managers or the IC designers at your customers to making changes in the design to make the thermal testing easier, or the control easier, right, more cost effective?
They're very receptive. Actually, there's a lot of work that we do with them on the assembly side. We have solution, and it's a joint design at the end of the day. So I'll say that it's a seamless cooperation. From that point of view, they understand the challenges, they understand what's ahead of us. So whatever solution we learn and we develop, we apply, and we work together. So.
Yep. And so if I could add to that, Andrei,
sure.
Because I work with the OSATs to provide the solution.
Sure.
So of course, so the customers aren't just going to dump a 1,000-watt part on you and say, here, test it. So we have to also work with you to develop that solution to test it. So yes, it's a partnership.
That's exactly what it is. And somewhere, I think the OSATs who provide a turnkey solution, they have some way of an advantage, because we know what we package, and we can make our life easier for test a little bit. So there is an advantage, but customer input and working with customer, the biggest thing we need to understand also from the customer, how we need to test it. And if you talk about automotive parts, we need to test them 100%. So that's a part that we need to make sure, because that's the time the spikes comes out. We need to know when the vectors need to be addressed. So it's a very tight cooperation. Did I answer your question, Rob?
Yes, you answered it very clearly. Thank you.
Okay, thanks. Moving forward, the same type of solution, it's applicable to memory. This solution is already in production. It has the same microchamber thermal conditioning approach, using the flex frame tray as a carrier. Again, it's an unlimited parallelism. When this particular solution, they go from -55 to 150 in one insertion. For memory devices. So it's something that probably should be looked more. Again, it's not a standardized solution. It's something that may need quite a lot of work to be embraced by the industry. And I'm pretty sure there are more concepts. People see the need, so there will be more than one concept to be addressed. I show you all the challenges that we had, but I just want to make sure you understand we well prepare. We have a lot of experience, and we have our toolbox with toolkits. So we have many leverage that we can pull, or levers that we can pull. So if you look at relative low power, massive parallel over 256, we do have our handlers already, thermal chambers. We can maneuver sockets in different ways to control temperature. And we have adaptive software that I think will become a critical tool, will be more and more sophisticated to be also predictable software. Same thing if we move towards higher power, around 50, we have the same similar solution. We also can use cooling of the PCBs for high power and a lot of liquid cooling technologies that come in place. So we well prepare for that also. We have more tools for more power. So our active thermal controls, as you saw, they go to 1,000 watts now. They will move towards 2,000 pretty soon, probably next year, around 3,000 watts. We know how to deal with sockets, pins. The software always helps us. And again, if it can be predictable, that will be much better. So we know what's to address what's coming. Again, we're in charge of the vectors, so we know when the vectors are coming. We start cooling the PCB, not only the front, but also the back, which is a very effective method of cooling, liquid cooling and refrigeration. So we have tools to apply. I mean, sure, we may need to customize, but we have a lot of levers to address those challenges. And as a summary, I addressed the high power devices. Characteristic would be low volumes, low parallelism, high power dissipation. They need to be addressed in tri-temp control, wafer level, final test, as well as system level test. MEMS sensor, very high volume, high parallelism, need to address the cost for those devices. Very uniform temperature requirements, and some mixture for the sensor, for the stimulus. Memory devices, high volumes, high parallelism, multi-temperature insertion, uniform temperature, and they have very long time at test. So you need to be keeping the temperature over a long time. We as an OSA that provide a variety of packages and also test, we're able to balance a very fine line between the thermal technology and the test economics. And again, we work hand in hand with assembly to get any help we can get in managing power dissipation when it comes to test. And with that, I conclude my presentation, and thank you for your time. And I'm guess open for question, Rob.
Yes. Thank you, Andrei. So there are some more questions. And the first is in regard to thermal resistance. What do you expect to have at the 2 kilowatt, 3 kilowatt area? Well, in order to provide thermal control, right? What kind of thermal resistance?
As close as possible to zero, to be honest. So when we touch the device, I show you a few methodology. The thermal provides it almost a perfect fit, because it has a tendency to mold itself over the package. Or for the thermal control, the surface is perfectly machine also is coated, and we use some extra help for some thermal paste or thermal papers. So I would like to have zero, and the reality is close enough and getting closer to zero.
Yep. Okay. Then another question. What is your experience with setup complexity, setup time, site-to-site yield type issues on the high parallelism solutions?
We did that day in and out, as you expect. We have hundreds of testers, so that's critical thing. I think in a relatively close environment, the way we manage it, it's not such a big concern. We're able to prove tester to tester, setup to setup. So I wouldn't say. I mean, I'm not saying it's easy, but I wouldn't see that as a big concern, and we address it as needed.
Yeah, I would imagine you have some kind of site-to-site correlation activity you have just to.
When you mention site to site, you mean a geographical site to site, or no?
In a parallel test setup.
Oh, absolutely. Yeah. We have a very well controlled process of that, and it's well managed and it's well controlled, and we keep monitoring that real time. And we monitor and also able to show to our customer real time how we monitor that.
Okay. And then last question, what is the response time of your active thermal when there is a high contingent current?
It's a fraction of seconds, it's milliseconds. Like I said, we are looking at a way to reduce that to zero by anticipating it. So if we can anticipate, will be real time, we can address it in real time. It's not easy, it's not there yet, but it's a must.
Yes. Okay, I think we've come to the end of Andrei's presentation. Thank you so much, Andrei.
I also want to thank our sponsors once again for making this event possible: Advantest, Amkor, Indium, FormFactor, and Nidec SVTCL. Advantest is a global leader in the ATE industry with over 30,000 installed systems using nanotechnology products to support leading edge process nodes with a large global workforce over 50 countries, working in environmentally sound processes. Amkor, who's providing OSAT services with a focus on technology, quality, and service, certainly advanced packaging, quality first, and service from design and test through drop ship, using a global footprint from around the world, but with local sales and support. And Indium, the premier assembly materials designer and manufacturer of thermal interface materials, solder paste fluxes and preforms, and certainly metals and compounds to solve challenging thermal problems. So once again, I'd like to thank all the sponsors. When you have an opportunity, please thank them yourselves to encourage them to sponsor more great events like Too Hot to Test. And so thank you very much for joining us, and I wish you a good rest of your day and look forward to having you participate at a future MEPTEC event. Thank you.